All right, so let's get right into. Hold on. I hope everyone can hear me.
Yeah.
All right, so today we want to talk about the Starknet architecture. So we want to look into the Starknet architecture. So what are those things that makes up the Starknet? So when you hear the word Starknet, you know there are a couple of components that makes it up. So we want to look at and understand each of those components, their roles, so that when you start hearing stuff like sequencer or app chain or STWO, like that, you won't feel that is the stacknet that these people are talking about, is it different from the ones that we learned? So firstly, the so that is an introduction to Starknet layer 2 access. So Starknet is a coordinated system. So with each component, so the components that we have sequencers, the provers, and the playing a specific yet interconnected role. So each of them they have their roles, and the roles are very specific, though interconnected. So although Starknet hasn't fully decentralized yet, so which means that currently Starknet is still a centralized system. So it's actively moving towards the goal. So this understanding of the role and the interaction within the system will help you better grasp the intricacies of the Starknet ecosystem. So let's have a high level overview of everything. So the Starknet operation begins when the transaction is received by a gateway. So which serves as the mempool. Now we all know what mempools are, right?
Yes.
Eh, So what are mempools?
Yeah, where transactions are kept temporarily until they are executed.
Okay, so it's like it's a queue. It's a queue of unexecuted transactions. So the transaction is initially marked as received. So which means that when it gets to the mempool, it is marked as what received. Then the sequencer then incorporates the transaction into the network state and tags it as accepted on L2. Final steps involves the prover, which executes the operating system on the new block, calculates its proof, and submits it to layer one for verification. So this is the simple. So we have the gateway, which serves as the main pool. So and the transactions are, they are sequenced. So when you say that they are sequenced, it means that they are arranged or they are ordered and then they are executed. So when they are executed, they are marked as accepted on L2. Then the prover the prover is now going to generate the proof. The prover will first batch and generate the proof. The proof will then be submitted to the layer one, which is the Ethereum. Now at layer one, the layer one will then update the state. The layer one is going to update the state root of the Starknet based on the validity of the proof that is sent. So the Starknet architecture, in essence, Starknet architecture involves multiple components. So we have the sequencer, which is responsible for receiving transactions. Or it operates similarly to validators in Ethereum or Bitcoin. So we know what validators are on Ethereum, right?
Yes, sir.
What are validators on Ethereum?
The I think execute transaction. They are the ones that create blocks and uh, I like add those blocks to the blockchain.
Okay, so how do they create blocks?
If you are using proof of stake in Ethereum, the
That's on
execute
Ethereum.
the sir.
I said that's what is used on Ethereum.
Yes, yes. So they execute the transaction and uh, so those transactions are batched into blocks. Then they are added to the network and is being broadcasted to other nodes.
Okay, so we know that the way the proof of stake works on Ethereum. Okay, let me ask you a question. Uh what's the consensus algorithm that is used on Ethereum? You guys just finished the Web3 class. Let's see. What's the consensus algorithm
Who was
that is
take? Who was take? Hello.
saying
Who was
consensus?
take? Yeah, who
I'm not
was
saying
take?
consensus mechanism. I'm saying the algorithm, not the
I
mechanism.
is it are you referring to like when to touch to touch of the notes in agreement to add
What's
a block to huh?
what's the name?
Ekarika.
What?
Ekarika.
Eterica.
Ekarika.
Ekarica. Ah,
Yes.
I've not heard about that before. No, I'm not
Yeah.
asking of your name, oh. Not your name. Oh. I mean the name of the
Oh, okay.
algorithm.
Oh, okay, okay, okay. Okay, like um, no, I don't think it's that short. I don't think that one is just that one is encrypted.
Yeah, the consensus algorithm is Caspar FFG now. It's Caspar friendly finality gadgets. That's the one that talks about the
So please,
uh,
can you come again with that name?
Caspar FFG.
Oh, wow, that's nice.
Mm. Caspar, the friendly finality gadgets. Yeah,
Yeah, I think I've heard that name once. So, like how exactly does it work?
how it works. And you've said it now. You said how it works.
Okay, the to third, reaching to third of the total message.
Exactly.
Oh wow.
So, you know that we have a validator pools, right?
Mm.
So and validator pools are before you can become a validator, you need to have some you need to have the execution client,
Yes,
the um a
the
full node,
execution,
the full node, and also this you also have staked there to ETH, right?
yes,
So then there's the random algorithm that is going to randomly select
yes,
sealed.
yes. They will randomly select nodes. Yeah,
Yeah. So
the
those people
validator.
that are selected, is going to choose a leader among them, and the leader is going to look into the main pool and is going to pick
It's
transactions
going to
from.
pick a block.
Yes, he's going to create a block and pick transactions from the member. So then the transactions will then be, is going to be broadcast to the other validators, and they are going to verify the transactions, and you know the two-third, like that. That's where the friendly penalty gadget comes in. So that's how blocks are produced on layer one. So in the layer two, on Starknet, so we use what we call the what uh, sequencers. So the sequencers, they are responsible for receiving transactions. So we already know that what the gateways, from here we already know that the gateways, that's what is serving as our main pools, right? So when the sequencer receives transactions, then it's going to order those transactions. Then it's going to produce a block. So it operates similarly to the validators on Ethereum. That's that. The prover. So we now, when you've executed that, it now sends the transaction. It's going to now send it to the prover. So that the prover is tasked with generating proofs for the created blocks and transactions. So it uses the Kairos virtual machine to run provable programs, thereby creating execution traces necessary for generating stack proofs. So, which means that it is the prover that now, the transaction normally it has passed. So, the prover will now generate the proof for those transactions. Then, on the layer one, which is Ethereum, it hosts a smart contract that is capable of verifying these stack proofs. The proofs are valid. The Starknet state root on layer one is updated. So Starknet state is a comprehensive snapshot maintained through Merkle trees, much like in Ethereum. This establishes the architecture of the validity rollup and the rules of each component. So for a more in-depth look at each component, we have freedom. So let's look more on the sequencers. So they are the backbones of Starknet network. They are like the Ethereum validators, they usher transactions into the system. So we have validator rollups excel at uploading some network calls like bundling and processing transactions to specialized players. This setup is somewhat like how Ethereum and Bitcoin delegate security to miners. Sequencing like mining demands F2 resources. So for networks like Starknet and other platforms utilizing validator rollups, a similar parallel is drawn. These networks outsource transactions processed into specialized entities and then verify their work. These specialized entities in the context of VACs are called sequencers. So instead of providing security as miners do, sequencers provide transaction capacity. So they order multiple transactions into a single batch, execute them, and produce a block that will later be proved by the prover and submitted to the layer one as a single compact proof known as a rollup. In other words, just as the validators in Ethereum and miners in Bitcoin are specialized actors securing the network, sequencers in validity rollup-based networks are specialized actors that provide transaction capacity. So the mechanism allows validity rollup to handle a higher volume of transactions while maintaining the security of the underlying Ethereum network. So if we look at this now, we already know that. So if we look at this now, we already know that the the TPS on Ethereum is around 15 transactions per second. So the sequencers on Starknet is what makes Starknet to be able to you know take in as much as over 1,000 transactions per second. So when it takes in those transactions, a lot of them, and it executes them, it orders them, produce block, execute them, then it's now going to take the block it's going to send it to the prover. The prover is runs the Cairo virtual machine, which generates the proof, the stack proof on those transactions, and the stack proof is then sent to the layer one, right? So sequencers must be reliable and highly available. So you see that sequencing, it collects transactions from users and order them, executing. So these are the things that a sequencer does. Sequencing. Sequencer, so which means sequencer, it's what it sequences. So sequencing means ordering of transaction. Executing means processing of transaction. Batching means grouping of transactions, and block production is, all the transactions that's batched together is going to produce a block for them. So sequencers must be reliable and highly available. So what's the meaning of reliability? So when you say that something is reliable, it means it is consistent, it is consistently good in quality or performance.
Yeah, it does not fail.
It does not,
It does not fail.
it does not fail. Um, is that it? Reliable is just about reliability is just about like it's just yes,
You can
dependable.
count on it.
You can count on it. Thank you very much. You can count on it. So it is very dependable. So then availability also, it has to be available. So as their role is critical to the network smooth functioning. So they need powerful and well-connected machines to perform their role effectively, as they must process transactions rapidly and continuously. So the current roadmap for Starknet includes decentralizing the sequencer role. So which means that currently the sequencer, we have just one sequencer, which makes it centralized. It is currently centralized. So shifting towards decentralized, we allow more participants to become sequencers, contribute to the robustness of the network. So when you say that a network is robust, it means that uh, it is strong and in good condition, and it's be able to withstand adversity. That's the meaning of what robustness. So do we all understand what is meant by what sequencers do?
Can you hear me?
Yes.
Okay, so you just said Starknet is centralized. Uh, can you expatiate?
Okay. So well, like the sequencers on Starknet, they are currently centralized. So centralization is just, when you have just one thing that is doing it, that's just the meaning of centralization. When you have one, if one entity is doing something, that means it is centralized. So which means that if that particular that entity, if it fails, then the network has failed. Do you get that? So decentralization means a lot of entities are doing it. A lot of entities are like nobody has the control. So everyone keeps their control. So and whenever we have a decentralized system like that, then there has to be a consensus mechanism. So which means there has to be a source of truth. There has to be a source of truth. Like how do you know if like three people are doing something? So there is possibility for disputes, or one of them can be a bad actor. So how do you resolve conflicts? That's where consensus mechanism comes in.
Okay, so I want to see sequencers as nodes in the layer one. So they are like nodes, right?
Sequencers, they are not,
Mhm.
they are like validators. Do you get? They are like validators on layer one. They are like the validators. So you said that the sequencers they do four things. Number one, they sequence transactions. They do what? They sequence transactions. What does that mean? It means that they order transactions. Just like validators, when you have validators, there has to be a leader amongst them, right? And it's the leader that is going to take up the transactions from the mempool. And when it takes up the transactions from the mempool, it's going to broadcast this to other ones. Then they are going to verify it, and the Casper finality, friendly finality gadget comes into play. So in this case too, so the sequencer, so it's going to order the transactions, Then it's also going to execute those transactions. Then after that, it's going to batch, that is, group those transactions together, and it's also going to produce block. So it's the sequencer that is doing all of those work, producing block. So currently there's just one sequencer
So,
on
sir,
Starknet.
what then does the prover does do? It does checks the transaction that the sequencer is bringing in.
What did you say?
I said the provers. What then is their work? Is it like they just check the transactions that the sequencer
So
is bringing in?
the prover is going to take in that block, and it's going to generate the execution trace for it. Generate the execution trace. You know, there is difference between execution and the execution trace. The sequencer, it executes the transaction. The prover generates the execution trace. The execution trace is used to generate the proof, which is sent to the layer one. So the layer one is going to verify. In the layer one, you have a smart contract that verifies the proof, and if it is true, it updates the state of Starknet on the layer one. Is there something still confusing? Is there anything still confusing?
No, it's fine. I think I'll just check more. But then I was still trying to get the graphs of the sequencer and stuff. But then I think I get the idea. Get the whole idea with sequencer being like validators, and then the provers checking it's just a little perplexing. But I don't want to draw the class back. That's why I'm just not wanting
Wait,
to.
what did you say?
Like I'm not really getting the whole scope of the sequencer. Like so, like I'll still like trying to fit it in. But since you said it's like a validator on the Ethereum network, so I'm just trying to like okay equate them together. But then that means that I'm just trying to relate where the provers now comes in. Like is it like they take the transaction and they start hashing there and stuff like that? Like it's just playing around in my head.
Okay, okay. Let's do it small. Hmm? The sequencer, it has just 4 functions, right? Number one is going to take, it's going to receive transactions from the gateway, which is equivalent to main pools or main pools. Now it will now sequence. Sequence means it will order the transactions. Then it's going to execute. So when you say that you are executing something, right? Executing is just when you execute a transaction, there's going to be a state change. Like if you execute a particular function now,
Yes,
you are just
yes, yes.
an
Change the
answer.
taste, yes.
So you will know if it runs successfully or not, and all the differences that it will bring about. So that one is execution. Now, execution is different from execution trace. Execution
Mm.
trace is you're looking at step by step, like the step by step of execution trace is about like showing workings. It's just like you're in a math class and your teacher asks you that x squared minus 5x plus 6 equals 0, that you should solve it. Hmm? So executing the solution will tell you that what x equals to 3 and y equals like x equals to 3 or 2. Let's say that x equals to 3 or 2. Now execution trace is going to be that you say uh subtract 6 from both sides. Add the square of half of coefficient of b to both sides. Find the square root of both sides. Subtract this from both sides like that. So that's like execution trace. So the execution trace is needed to generate the proof. So that proof is what is now sent to layer 1. So the proof is what tells us that what the sequence is correct. What is correct. So which means that you don't have to be rerunning everything that the sequencer has already run. You don't have to be rerunning it on the layer 1. It just validates that okay, the proof is correct and it updates the states.
Makes sense. Makes sense. Yeah, I'm getting it.
All right, thank God. So then we now have the prover. Where is the sequencer? Okay, the prover. So the prover serves as the second line of verification in the Starknet network. So their main task is to validate the work of this. Do you see that? Their main task is to what? Validate the work of the sequencers when they receive the block produced by the sequencer and to generate proofs that these processes were correctly performed. That so what they do is they validate work of the sequencer and generate proof. Now, the duties of a prover include one, receiving blocks. See what? Hey, you people are sleeping.
No, I'm here, sir.
Sequencers receive what?
Transaction.
Transactions. Provers receive what?
Blocks.
Blocks. Thank you. So they receive block. So block provers obtain blocks of processed transactions from sequencers. Now, processing. So provers process these blocks a second time, ensuring that all transactions within the block have been correctly handled. Then proof generation. After processing, provers generate a proof of correct transaction processing, sending proof to Ethereum. Finally, the proof is sent to the Ethereum network for validation. If the proof is correct, the Ethereum network accepts the block of transactions. So provers need even more computational power than sequencers because they have to calculate and generate proofs. They have to calculate and generate proofs. So if you look at using that as an example again, x squared minus 5x plus 6 equals 0. So x squared minus, it is possible that you can, if they ask you to solve it, it is easier for it to solve you can solve it than to prove that you solve it correctly. So that's the difference between the sequencer. So the sequencer will just solve it and get the final answer. But the prover is going to make sure that, okay, what the sequencer did is correct. Then it will now generate a proof of execution. Proof of execution. So the design of Starknet relies on these two types of actors, sequencers and provers, working in tandem to ensure efficient processing and secure verification of transactions. So then talking about optimizing sequencers and provers, debugging common misconception. So the relationship between sequencers and provers in blockchain technology often sparks debate. The common misunderstanding suggests that either the prover or the sequencer is the main bottleneck. To set the record state, let's discuss the optimization of both components. So Starknet, utilizing the Cairo programming language, currently supports only sequential transactions. So plans are in place to introduce parallel transactions in the future. However, as of now, the sequencer operates one transaction at a time, making it the bottleneck in the system. In contrast, provers operate asynchronously and can execute multiple tasks in parallel. The use of proof recursion allows for task distribution across multiple machines, making scalability less of an issue for provers. So since the asynchronous and scalable nature of provers, focus in Starknet has shifted to enhancing the sequencer's efficiency. So this explains why current development efforts are primarily aimed at the sequencing side of the what of this equation. So if you hear tomorrow or next tomorrow that uh, Starknet if you see in the roadmap of Starknet that there is something called what? Transaction parallelization. Hmm? Do you understand what it means now? Do you understand what it means?
Yes.
Yes, yes.
Transaction parallelization. So which means that currently on Starknet, the sequencers undo or they execute the transactions one after the other, like one transaction at a time. So, but the what's it called? The prover. So the prover, because it has recursive proof, so it means it can, you know, it can distribute its tasks and asynchronously prove a particular block. Then we have nodes. When it comes to defining what nodes do in Bitcoin or Ethereum, people often misinterpret their role as keeping track of every transaction within the network. This often is not entirely accurate. Nodes serve as auditors of the network, maintaining the state of the network, such as how much Bitcoin each person owns or the current state of a specific smart contract. So they accomplish this by processing transactions and preserving a record of all transactions. But that's a means to an end, not the end itself. So in validity rollups, and specifically within Starknet, this is somewhat reversed. Nodes don't necessarily have to process transactions to get the state. In contrast to Ethereum or Bitcoin, Starknet nodes aren't required to process all transactions to maintain the state of the network. So there are two main ways to access network state data: via an API gateway or using the RPC protocol to communicate with the node. So operating your own node is typically faster than using a shared architecture like a gateway. Over time, Starknet plans to duplicate APIs and replace them with a JSON RPC standard, making it even more beneficial to operate your own node. So it's worth noting that encouraging more people to run nodes increase the resilience of the network and prevent server flooding, which has been an issue in network in other layer tools. So currently, there are primarily three methods for a node to keep track of the network state, and you can have nodes implemented in them before the number one, replaying old transactions. Number two, relying on L2 consensus, and number three, checking full validation on L1. So each type of node setup comes with its own set of admin requirements and trust assumptions. So nodes that replay transactions Notes that replay transactions require powerful machines to track and execute all transactions. So these nodes don't have trust assumptions. They rely solely on the transactions they execute, guaranteeing that the state at any given point is valid. So these ones they require they don't have trust assumption. So they rely solely on transactions they execute. So that's for the first one. They have to replay the transaction. So nodes that rely on L2 consensus. So nodes relying on L2 consensus require less computational power. They need sufficient storage to keep the state, but don't need to process a lot of transactions. So the trade-off here is a trust assumption. Currently, Starknet goes around one sequencer. So these nodes are trusting Starkware not to disrupt the network. Trust me, bro. However, once a consensus mechanism and ledger election amongst sequencers are in place, these nodes will only need to trust that a sequencer who state is not network is now check nodes that only update their states based on proof validation and L1 require the least hardware. So they have the same requirement as an Ethereum node. And as Ethereum Light nodes become a reality, maintaining such a node could be as simple as using a smartphone. So the only trade-off is latency. Proofs are not sent to Ethereum every block, but intermittently. So resulting in delayed state updates. Plans are in place to produce proofs more frequently, even if they are not sent to Ethereum immediately, allowing these nodes to reduce their latency. However, this development is still a way off the Starknet ecosystem. So, conclusion. hmm, Through this chapter, we delve into the Starknet structure, uncovering the importance of sequencer, proven, and nodes. So, and each has its own unique role to play. So, and as we venture further into the Starknet universe, our next topic will be exploration of transaction lifecycle before we delve into art of coding. So, do we have questions based on these ones?
Yes, sir. Does Cairo use blobs, or does Starknet, sorry, use blobs?
What?
Does Starknet use blobs?
Sorry, I didn't get.
Does Starknet, do they use blobs? Like, do they
Oh,
use
oh,
blobs?
oh, okay, okay. Yes, they use blobs.
So if they use blobs, then I'm still trying to understand. I understand that the prover receives the block and does a kind of calculation to ensure that all the transaction in the block have been properly well documented or well checked by,
Sorry,
or
I
well
don't get
carried
your
out.
question very well. Can you ask
Yeah,
it again? The first question.
I'm I'm asking if Starknet use
Blob,
blob.
blob.
Yes.
Yes,
Yes, so like I'm now trying to understand if Starknet use blob, I mean, and then like blob or blob.
yes.
So if Starknet use blob, meaning that each transaction is coming in or will be sent to the layer one as a blob. So like is it like it is when it is before the prover checks through the block of transactions or confirms the transaction that it is now converted to a blob, or before it gets to the prover, at what point like does it convert it to a blob before it finally goes on the L1 on the L1?
So, thank you very much for that question. It shows that you very much understand what's happening. So, firstly, let's understand what a blob is. We have normally the normal way of transacting is, you can make use of what we call the core data. We all know what core data are, right?
Yes, sir. Yes, sir.
Um, so when you now say blob, blob is much more different. Hmm? So in fact, the first time that blob is like, it's blob you can send image. You get, it's like the data format in which images are even sent, and you know how big that can be. So now let's just run through the Starknet architecture again, and let us think, if there is blob in Starknet, where can it be? So we know that there is gateway, which is like the main pool where the transactions are sent. So, and the sequencer sequences them and executes them, and um, you know produce block, and the sequencer produces block, and this block is now sent to the prover. Do we get? Now, the prover that gets the block, now that block is now re-executed, and the execution trace is used to generate proof. Now the proof is now sent to layer one. Before, huh? Before the is it decorum or is it dencom? Yeah, I think it's dencom fork. Before the dencom fork, so the only way to interact on the layer one is by using what we call the core data, right? So at the during the DENCON fork, with the EIP 4, is it 4844? So that's where we have the introduction of blob. So with the blob, layer twos can now send their proofs, to layer one using blob. So which separates their own gas fee competition from the normal users, and that greatly reduced the fee that for the chains on layer one. And that's the reason on Starknet currently, the um on Starknet currently, the transactions are very, very as low as a cent for uh, running transactions on Starknet, and that's because of the DEMCON fork, or the introduction of the EIP 4844, which allows the use of blocks in communicating with the L1. So you can already see that it is the prover that is going to be sending its own proofs as blobs to the layer one.
Yeah, makes sense. So that means that how does the layer one now confirm that what the prover has sent to is correct? And I understand that the prover have done, like, this is my question now. Now before the then come fork. Now the layer one has a way of interacting with layer twos, and they just do that stuff, get transactions, or probably let's leave out layer two per all. They get the transactions and then go through the verify the transaction and all those stuff. And now, instead of transactions, they're now getting blobs. They're now getting proofs. Like since the proof have proof trace. So do the layer one also have their own proof trace to be able to follow up and check
Wait, what did you
what the
say?
proof,
Did the layer one also have their what?
like, do they have a kind of like proof trace to be able to ascertain the proof that the layer two is sending to them, or how exactly does the layer one confirm this transaction? Before the layer one have their checkers, their validators that will validate these transactions and stuff like that. But now they are receiving proofs. They are receiving proofs. So how do they confirm all the transactions that have been proven? What if layer two is a kind of thief that is trying to manipulate something and is sending it to layer one, something like that? Like,
So that is where ZK proof comes in. That's where ZK proof comes into play. So I'm going to try to be slow. I think I've been slow actually. But what I just want to say is, if I'm going to be saying some things, if you don't understand, just continue to be asking questions. I believe it's going to be a net positive effect or learning experience for everyone. So yeah, when we talk about, the reason we have Starknet and other layer tools is so that we can solve a particular problem. So there is a problem that we have with decentralized systems, which is that number one, we have what we call the blockchain trilemma. The blockchain trilemma, which is that a blockchain cannot be decentralized, secured, and secure, right? So so it cannot do all of those things. Now, we now have Ethereum, which is decentralized and it has a very big security, but it has 15 transactions per second as the as its throughput. So we now have different ways in which you can scale Ethereum. So there are different ways. We now have what we call the roll-ups as one of the ways in which you can scale Ethereum. We now have two types of roll-ups. We have what we call the optimistic roll-up and what we call the validity roll-up. So when you say that something is optimistic, you are optimistic that you know you are just optimistic. Optimistic is like you have an inherent good behavior unless you prove it otherwise. So what this means is that if I'm giving you money, right, you are optimistic that the money that I gave you is what is original, right? Unless there is a unless someone tells you that what this money is what is fake, that's when you can now start saying that, oh, because there's no way someone will just give you money and you're like, ah, this money is fake or something, unless you are, you know, you are first optimistic that, oh, you don't even check most of the money that you collect when you collect the money. So it's when you now realize that, or someone tells you that, ah, this money is fake, you now start going back to, there's going to be a contesting. So for optimistic proof systems, for optimistic roll-ups, they usually have the contesting period, which is that when a transaction goes on, you have a particular period for you to contest that this transaction is right or wrong, or there is a fraud case. So, and it's going to be, well, when you now say that something is what is validity, it means as you are sending the transaction, you are also sending the proof that this transaction is what is correct, right? So for validity rollup, just like I've mentioned, the prover is going to send the proof that the transaction is correct. Is going to send it to a contract on layer one, and that contract is going to verify that it is true. So if it is true, it's going to update states of Starknet on the layer one contract. It's going to. So if it is not true, it will not. It will not. You might be thinking about how is it that how will he be able to generate proof and all of those questions? If you have specific questions about,
Yes, yes,
yeah,
yes.
that one is a lot of mathematics.
Because
Like
because because you just mentioned that it isn't zero knowledge. That means it does not know what is coming, or it does not
when
know
we
this thing,
say
but yet
zero
it's able to
knowledge,
verify.
so when we say zero knowledge, it means that zero knowledge there means that it doesn't reveal any other information apart from the fact that this thing is correct. It doesn't Zero knowledge means that it doesn't take in any information about it. The only information that you can only derive from it is the fact that this is correct. In fact, when you say Cairo, I think I mentioned it when I started taking the Cairo class. Cairo is this one is we say proof of correct execution. That's what you do with Cairo. Proof of correct. And Cairo is a provable programming language, which means that when you write a program on Cairo, if someone executes that program, they can generate proof of correct execution. In fact, they can generate proof of execution for that program. They can generate proof of execution for that program. So when they generate proof of execution for the program, the next person don't need to, re-execute it. You just need to make sure that, okay, the proof, you just need to check that the proof is what is correct. If you want to understand how everything goes, to oof, can I hope everyone can hear me, Sha?
Yeah, I can hear you now.
Yeah.
Can hear
So
you now.
someone was raising his hand before. I think Emmanuel. Okay, okay, okay.
Yes, it means that with Cairo programming language, there's no need to learn ZKPs now, the technology of the art of
ZK.
Ps, zero knowledge proofs.
Yeah. So this, when you have about learning ZK, when ZK, like talking about building on Ethereum. You can build on Ethereum at the application layer, or you can build on Ethereum at the protocol layer. So at the application layer, you just learn about Solidity and how to write Solidity. At the protocol layer, how do you even build the Solidity itself? How do you build the architectures and all of those stuff like that? So that one is different. Those are two different things. So when you talk about Cairo, yes, Cairo, with Cairo, you can write provable programs. With Cairo, you can write provable programs. So it's just like you are the consuming end of it. Because if you now want to understand what happens in Cairo, if you want to understand what happens in Cairo, then you need to learn a lot of things. Number one, you need to learn a lot of things. The Cairo itself, what does it do? Cairo means CPU algebraic intermediate representation. So which means that when you write, the way Cairo works is different from the way normal programming languages work. When you run normal programming language, when you run Solidity, for example, Solidity runs on the Ethereum virtual machine, which is more like a virtual machine like the normal, which is more like the normal way computer programs run in binary. It's in binary. But for Cairo, it's different. In Cairo, it is when you have Cairo, you are going to convert the Cairo to what? To Sierra. Sierra means safe intermediate representation. So the safe intermediate representation, what it does is that it makes sure. So it's actually in Cairo one that you now have the introduction of safe intermediate representation, which means that with safe intermediate representation, you can, when you write a program in Cairo, it cannot fail. There's nothing like panic or anything. The program cannot fail. That's why when you write your smart contract and you build it, it's going to produce the what? The car, this Sierra and then the Kazim. So those ones, they cannot fail. They cannot fail. So when you have those ones that cannot fail like that, that's like the starting point of of your transactions. Now, in the Cairo version, in the verifier also, there are some things that it's also looking at. So actually, if you want to understand most of those things, you need to take the Cairo white paper and read the Cairo white paper. When you read the Cairo white paper, you are going to understand a lot of things about the architecture. It uses the read-only model. So, like, normal in the normal computer, you'll be able to like read and write, but this one you can only read. So instead of how do you now write? It's another way. So you understand the meaning of ints, you understand the meaning of you have ints, you have what again? We have ints, we have, oh, I've forgotten the name of that other one. But if you read the Cairo white paper, if you want to understand what happens behind the wood, like the proof that is generated, how does it generate it? How does it, do all of those stuff? Then you need to go deep into the Cairo white paper for you to understand all of those ones. But right now, what you need to understand is that when the programs that you write, all the programs that you write, they are represented as what? Safe intermediate representation and can be proved. So when you run a particular program, it's going to run it and generate the execution trace. And that execution trace is now used to generate the proof, which is sent to a contract that verifies it. So the way it verifies it is that when you send all of it, in fact, the things that are verified there, we have it's going to take the PC, like the program count at the PC at the beginning, the initial state, all of those stuff like that. So yeah, yeah, you can someone is raising and you can talk.
Okay, so like now this like a little deviation out of the talk. Now, as well that I was trying to just start to probably maybe write a simple smart a simple smart contract using Cairo. And now it's now dawned on me that one, I don't have a VS Code extension telling me when I'm wrong and stuff like that. I know that one there will be an extension. So I don't want to use try to ask if I can get if you can suggest an extension that can be checking my code for me, like while I'm writing that. But that's by the way. The major question I want to ask is this: is there something like Remix for Cairo that you can use to check your contract, compile it, and then deploy it and be able to check out the function? Because right now, as I'm writing the contract, I'm just realizing it's dawning on me that I have to write the tests too in order to be able to test the contract. So like, is there a way out, or that's just the way it has to be for now? Like, I have to just write the contract and then write the test for it. Then please, back to the question one. Please don't forget the extension that will then mark out all those ones that used to show red line when you're writing nonsense. Because I'm expecting my own contract to have a lot of red lines.
I did not get the last question.
No, like I'm saying, don't forget my question on that you should help suggest an extension that one can use in VS Code that will show all those red lines when you're writing nonsense. Because my code now is
Yeah,
supposed to be showing a lot
one
of.
extension. There is Cairo.
I'm using Cairo 1, but it does not show any red lines
Doesn't show.
when I'm
So
writing.
the reason it's not showing the extension is most likely because you have not set it up yet. Most likely. So either it's just like Rust also. In Rust, if the code that you are writing, if it's not connected to the main crate, to the main this thing, it's not going to show you if it is wrong or right. So which means that whatever
So
code that
how do I do it?
so let's say okay, let me try to stop presenting. So let's say I am so let's say I create a what's it called? Scarp new let's call this stack app. Okay.
Does it matter that I'm using SM Forge instead of CAP?
It doesn't matter. So you see this leave.cairo here. This is like the main entry point of the contract. So if I am writing a contract, if you are writing a contract inside this place, it should tell you if what you are writing is strong or not. Unless if the extension is.
I'm not seeing the lib.cairo, sir.
This is lib.cairo. Or you don't have lib.cairo there.
I do have lib.cairo. Like, I'm not seeing where your arrow is going. That's what I'm saying. But like the thing is, I'm not writing exactly inside lib.cairo. Like inside my lib.cairo, I just wrote mode, then the name of the file that I'm writing inside. So I created a new file and I'm writing inside that file.
Yes.
But
So
my lib.cairo is like,
if you have another, so let's say that you have something here. You have, let's say, contracts. So if you have contracts here, and inside this place you now have, let's say it's in this place that you have ALC 20, ALC.Cairo, right? So you know that normally in this place now you're supposed to have a lib.Cairo here. How does the directory structure work here? So, and in this place, what's the name? ALC.
So your screen is paused too.
What?
Your screen is paused. It's on
Yeah.
Node.js Starter Pack API. It's on Starter Pack API.
I don't get.
What,
Your
what,
screen is what we are saying
what
now
you're
is
saying is your
Starter Pack
terminal.
API.
Oh, sorry. Let me check. This one it does the obvious sometimes. What are you guys saying now?
Infinity Mirror.
Infinite mirror.
How about now?
I see some.
Yeah, we can see the lib.Cairo now.
Okay. So you need to have that contract in this. You have to have it scoped here.
Your screen
So if
is your font is tiny.
So it is when
Thank you.
it's in this main here, that's when if you are now writing a function here to now start that's when it's not going to start. I don't even know if, let me check if Cairo extension. Cairo is, though that Cairo one also at times it doesn't really show something. Okay, it is installed, so it's going to start showing error where necessary. Or just use what's it called? Scarp build.
Okay,
So
so even if I use SMForge to create the project, I can use Cap Build to.
I use SM4, just follow their own instruction also. Just follow their instruction. So this one now, module not found. Sure. Does it work this way? So I think this thing here is supposed to hey out. So, yeah. Okay, yeah, you're supposed to have contracts.
I was thinking that would be mod ELC dot Cairo, like the complete name of the file. I don't know,
No,
just
Cairo is not supposed to be there.
oh, okay.
But should be something around this. Actually, I'm going to recheck it to see also. Okay. Let's see. Okay. So leave those guys of 15 happen. Missing semicolon. Split stroking. Oh, I can't figure this out. But the reason most likely it doesn't show is if it's not in scope. So if that contract is not in scope, just find a way to bring it in scope and everyone will be fine. Okay. So let's look at the transaction versions. Where is this? Yeah. So understanding Starknet transaction types is essential to mastering its architecture and capabilities. So each transaction type serves a unique purpose, and getting a grip on their differences is crucial for proficient Starknet usage. So Starknet OS, the backbone. So central to Starknet functionality is the Starknet operating system, a carrier program that fuels the network. So this OS orchestrates key activities, including one, deploying contracts, two, executing transactions, facilitating L1, L2 message exchanges. So in Starknet terminology, protocol level alludes to modifications in the foundational Starknet OS carrier program, ensuring a step-up process. So we have transaction types, declare transactions, so unique in their ability to introduce new classes, leading to potential new smart contracts. Then we have invoke transaction, so they call upon an action but can't introduce new ones. Deploy account transactions, so designed for setting up smart wallet contracts. So declare transactions, so these are the transactions are the sole mechanism for introducing new smart contracts to Starknet. So if you want to deploy a smart contract on Starknet, then you have to firstly declare the transaction. So when you declare it, it's going to give you the class hash. Then you can now use that to deploy the contracts. So you see that in the core programming in C++, before employing a variable or function, it's first declared, signaling to the compiler its existence and type. Only then can you define or use it. Declare transactions in Starknet operate on similar principle. They announce a new operation, prepping it for future. So we have version 0 suited for Cairo 0, version 1 tailored for Cairo 0 with nonce. And we have version 2 optimized for Cairo contracts, modern Cairo contract. So here is a key distinction to understand the difference between the Cairo versions. With Cairo 0, developers sent Cairo assembly code directly to the sequencer. But with the contemporary Cairo version, they send Sierra code to the sequencer. So breaking it down, Cairo 0 compiles straight to Kazan, while the current Cairo version compiles to Sierra, which subsequently compiles to Kazan. The crucial difference is that Sierra executions are infallible and always provable, whereas in Cairo 0, transaction could fail if they did the non-provable. The latest Cairo iteration ensures all code compiles to Sierra, making every transaction reliable. Do we understand that? I believe I have explained it previously, right?
Yes, you did.
So no question, right? When declaring a contract with the latest version, developers are essentially announcing Sierra code, not just raw cousin. Examining the parameters of a V2 transaction reviews measures that ensure the class hash corresponds to the Sierra code being dispatched. Class hash incorporates the hash of the Cairo assembly code. But since developers send Sierra code, it's imperative to ensure that the dispatched code aligns with the indicated class hash. So in essence, using the most recent Cairo version implies the utilization of the latest declared transaction version. So the invoke transaction, unlike declared transaction, invoke transaction does add new functions. They ask the network to carry out actions such as executing or deploying contracts. This method contrasts with Ethereum, where a contract can either be deployed by sending a distinct transaction or by having another smart contract factory to deploy it. Starknet uses only the second method. So the universal deployer contract in Starknet illustrates this idea. So utility helps to deploy contracts. This mirrors how in C++ a declare function is used to perform tasks. So in computer science, think of how functions operate on C++. After declaring the function or object, you invoke it to take action. Starknet invoke transaction works similarly, activating pre-declared contract of functions. So every invoke transaction in Starknet undergoes validate and execute stage. What did you hear? Am I still here? Oh, Victoria.
Yes, sir. Yes, sir.
What,
This class hash, right? Is it the hash of the module?
is it the
Is that what it is? The hash of the module? Because I'm trying to understand what's the hash to get the class hash.
okay? So when you declare a transaction, I mean when you want to deploy a contract, right? So you are going to declare the contract. So the class hash, the hash is the hash of the contract. You know, the contract, the way the contract is, you hash it, you now get that hash of the contract is what is called the class hash in this case. And that there's actually a reason. Starknet is also using class hash in that case also. If you read the Cairo white paper, you understand it.
Okay, so when you say the hash of the contract, so is it that the whole code was hashed
The
where
whole
the
code
class
was
hash?
crashed. Yes.
The whole Cairo code.
Yes.
Just like
Okay.
byte the solidity.
Exactly. So which means that if you should change, which means
Sorry.
that you have two, you cannot deploy the same contract twice. You cannot declare, not deploy. You cannot declare the same contract twice. So if you declared a particular contract before, and you now declare that contract again, it should give you the same class hash and tell you that oh, it has been declared before. So and if you see the already declared contract, even if you are not the one that declared it, you can still deploy it. So which makes sense. It's that on Starknet, if you want to verify a contract, you just have to verify the declared Sierra. So when you verify that, just that one, it applies to everything. Though on Ethereum, it makes sense too that when you verify one contract, if it's a factory contract, it's going to automatically verify other ones also. But this one is still it still makes more sense. And when you um, when you read the Cairo white paper also, you know the reason why it's using the class hash. It uses that class hash the, uh, to load the particular contract. If you want to call a contract, you just use the class hash to load that contract.
Okay. Okay. So in terms of my address, my account on Bravos or Agent Wallet that I deploy, right? So is there
Yeah.
a code that has been set already that
Yes,
deploys these addresses?
yes. So that's the whole. Now, if you now look at this, is that deploy account way to every look at this. Every invoke transaction in Starknet undergoes validate and what execute stages. Do you get that?
Where are you reading?
Shade not sleeping. Every invoke transaction, shade not see it.
Can you highlight it?
This is it. Can you see it?
Yeah, thank you.
You cannot see it, Abby.
No, I can see it now.
This one.
Who's okay. That's
So
covered everything. I can see.
okay. So we've talked about declare already, right? We said that there are three types of transactions: declare, invoke, and what deploy. Abi now,
Okay. Yes.
it's like if people are already sleeping. Or you want to sleep?
No, we are here.
Oh yeah, yeah.
So the second one is now the invoke. So they are telling us that every invoke transaction in Starknet undergoes what? Validate and what? Execute stages. The validate step checks the transaction's correctness. Similar to a syntax or logic check after validation, the execute phase processes the transaction. After that, this two-step process, focusing on utilizing existing functionality, highlights Starknet's distinct transaction strategy. If you want to put invoke a particular transaction on Starknet, well, this one it passes through validate and what and execute. Now, on Ethereum, if you want to call a particular contract, you just call it directly. But in Starknet, it uses what we call the native account abstraction. What does that mean? Since there's no difference, there's nothing called externally owned accounts and something, something, something. So, which means everything on Starknet is what? Is a smart contract account. Which means that your wallet, the wallet that you are making use of on Starknet, is a smart contract. So, and for smart contracts, for account contracts, they usually have what we call what? They usually have this validate, this execute function. They usually have it. So, which means that is that execute function. When you want to call, when you want to invoke a particular transaction, it's like you are invoking, you are calling the execute in your own smart contract, your smart contract account. It's now your smart contract account that will now call the contract for you. So it is your smart contract that will now call that account for you. Do you get? So
Yeah.
that's how things work in Starknet. So deploy account transactions. Look at this. The challenge arises: how do you set up accounts without having one already? Mhm. Because we've already said it here that you have to validate and what and execute. That's when creating your first smart wallet contract, deployment fees arise. How do you cover this without a smart wallet? So the solution is deploy account transactions. Uniquely in Starknet, addresses can accept funds even without an associated smart wallet. So this trait is pivotal during deployment. Before an account is formally created, the validate function checks the proposed deployment address, even if it lacks a smart wallet for sufficient funds. If present, the constructor proceeds, resulting in account deployment. So the method guarantees the new account legitimacy and financial rating. So which means that when you want to create a new account, the first thing you do is what you already have an address. Hmm? Even though it is not deployed yet, you already have an address. So you have to send funds into the address first before you can now deploy it. So conclusion, it's pivotal to understand each transaction type, declare transaction standout for their rule. Please, do you have questions as regards the transactions?
Yes, sir.
We are asked.
So just like we have in Solidity, where we can get ABI once we compiled a contract. This class hash, is it possible to get it probably maybe let's say we compile the contract through a script, and we compile the contract through a script, and we deploy the contract through a script rather.
Yes,
Is there a place we can get the class hash? Is there a place
yes,
it is stored to?
yes, yes.
Under what section? Like when we deploy, under what section is it?
So actually,
Do we find it?
when you declare a contract, when you declare a contract, you don't it and you when you declare a contract, the when you declare a contract, you already see the ABI is already part of the information that you see on. Um, you can just go to agents. You can just go to Voyager and you get your ABI for that contract from. So then, what was it again? Then, yes, there is actually another this thing too. There is a there is something that you can press. There is a this thing there. You can check it, sha, but there is a CLI command that you can get and it will give you the ABI. Do you do you get?
Yes, sir. Yes, sir. I'm following. Although I was talking about when I'm talking about contract, I was talking about probably maybe say not like a wallet own, or it's just say maybe a random contract that I write on my own. Like if I deploy it, like is it possible to retrieve the class as something like that? That was what I was
Yes,
actually asking.
it will give you the class hash. when you declare it, go and check the when you go to the network to check it. You see the API also.
Okay, because why I'm asking this like this is because
You can
we
use these are to Starknet
sir.
RPC builder. You can use the Starknet RPC builder. Let me check.
Okay.
Page,
Okay, because why I asked this is there was a course that just wrote a script and they just did npm run deploy direct and using that script and they did not probably maybe inside the
run the
script maybe they declared it and everything.
declare and deploy. There is declare and deploy. If you are
Okay,
using what's
probably
the
maybe script
if you are using this
JavaScript.
no, Starknet JS, Starknet JS, there is declare and deploy there also.
Okay, because inside the script, probably maybe they declared and then deployed inside the script, but the command they used for deploying was just npm run deploy and npm run deploy, something like that. Can't really remember, but npm something, sha. So like, but like where I'm going to is if say I'm able to write such a script and deploy the contract, where can I go? Like under which file or something can I go that I will get
You
the
have
class
look at
hash?
something. You can class get class is it this Starknet this let's get class at. So if you should send this request, okay, this one is answered. Let me go to the notes. So you see that if you want to get
So
if
what
you
we are
put
seeing is transaction lifestyle, transaction life cycle.
oh sorry. Okay, so this one now you can see it gives you the Sierra program, gives the Sierra program, and it also gives you the API. See, this is the API of the contract. So any other question?
Yes, sir. I've, okay, I have a question. I don't know if you can hear me.
Yeah, I can hear you.
Okay, let's say for deploying an account on Starknet, is it that we have to deploy for every network we're using? Let's say I want to work on mainnet, I have to deploy that particular account on mainnet. I want to work on, let's say, Sequoia, I have to deploy the account on Sequoia, or if I just deploy it once, it's deployed.
You have to deploy it where you want to work, where you want to work on.
Right, right. Thank you.
You're welcome. Okay. So no other question. So we move to transaction lifecycle. I think we've already talked about the right. So starting a project is transaction instance. A transaction starts by being sent to a gateway, a node, which acts as the mempool. The sequencer currently is single service. first validates and then executes the transaction in order. If validated successfully, the status becomes received. If not, the status becomes rejected. Successfully executed transactions are applied to state and marked as accepted on L2, which during this phase are reverted. So then in the prover, so in the prover stage, the system operates on the new block, completes its proof and sends it to L1. So the following image shows the transaction flow. So we have the mempools, if the validation, if the transaction is received, marks as if validation fails, it is rejected. So from here, it's either accepted on L2 or reverted. Then here it's either accepted on L1 or reverted. Then, before exploring each step in depth, let's clarify the different transaction status. So each transaction has two primary status types. So we have the finality status and the execution status. So in the finality status, we have received the transaction pass mempool validation, but hasn't included in block. Accepted on L2 and accepted was added to block on L2 and L1. So execution status, we have rejected, reverted, or succeeded. So we know rejected from what's it called, mempool, reverted at the execution side, succeeded. So to obtain this information, query the transaction receipt found by the node. Refer to the tooling chapter in the Starknet book for methods like the transaction receipt, command in Stackline, or the first transaction receipt method in the Starknet file library. We will use these tools throughout this chapter. All right. So nonces in not nonces. Nonces in Starknet. What are nonce? Nonce. What are nonce?
Like identifiable digits, like a digit to identify a transaction.
Mhm. In on Ethereum, nonce can mean two things. What and what?
It can mean the order with which the transaction is being executed, I think. And also used to what's that word now? Let me let another person just try.
In
Used to
relation in relation to proof of work, what are nonce? No, it doesn't automatically deploy you. Once you fund it, you still have to deploy it. No, when you send funds to the address, what you want to say is when you send fund to it, you cannot send fund out of it. So when you try to send fund out of it, it will first deploy it first before it will now send it. Maybe that was what you meant. But you have to deploy first before. Okay, nonce. So in relation to proof of nonce can be, the nonce in your wallet, the nonce that is included into your transaction is going to be the number of transactions that you've performed with that particular wallet. It's added and it's used to other transactions. Nonce in relation to proof of work. For proof of work, you need to find the block difficulty, right? And the block difficulty is just solving for the hash of the transaction or the block to have a so number of for the hash to have a particular number of zeros either at the beginning or at the end. And in order for you to do that, you vary the nonce value. So you vary the nonce value for you to be able to get that. Just so nonce in Starknet. Initially, Starknet did not incorporate nonces. This omission meant that the same transaction could be sent multiple times with an identical nonce, leading to duplicate hashes. A problem. In Ethereum, nonces not only sequence transactions, but also ensure each has a unique hash. Similarly, Starknet employs nonces to assign existing hash to every transaction. Starknet's current stance on nonce mandate that they may be sequential. In other words, when transferring a transaction from your account, its nonce must precisely follow the previous transaction's nonce. Although nonce abstraction would allow developers to manage this logic at the smart contract level. Starknet is reviewing this feature. However, its implementation is not deemed a priority. Transaction creation. The other start with its preparation, the sender queries the account nonce, which acts as a unique identifier for the transaction, signs the transaction, sends it to their node. So the node, analogous to a post office, it sees the transaction and broadcasts to the Starknet network, primarily to the sequencer. As the network evolves, the transaction will be broadcasted to multiple sequencers. That's when the what's it called? When the transaction is communicated. The sequencer, the gateway performs the validation step. So that checking the maximum fee exists a minimum fee, and the account balance is greater than the maximum fee. The transaction will be saved in storage if the validation function passes. If not, rejected. The sequencer's rule. You can see like we are repeating the same thing. So if at the end of this class, you don't become a Starknet Maxis, like there should be nothing in Starknet that you don't know about. Abina, on receiving the transaction, the sequencer acknowledges its receipt but hasn't processed it yet, similar to the zero input state. So you see the transaction, validates it, execute it, update the state. So remember, standard process especially, the nonce won't change until the sequencer processes the transaction. This can complicate backend application development, potentially causing errors if sending multiple transactions consecutively. Then we have accepted on layer 2. So finality status accepted on layer 2. Execution status succeeded. So we can see the difference between finality and execution status. So accepted on layer 1. Transaction finality in Starknet. So transaction finality refers to the point at which a transaction is considered irreversible and is no longer susceptible to being reversed or undone. It's the assurance that once the transaction is committed, it can be altered or rolled back, hence securing the integrity of the transaction and the system as well. Let's dive into the transaction finality in both Starknet and Ethereum and how they compare. So Ethereum transaction finality. Ethereum operates on a proof of stake consensus mechanism. The transaction has the finality status where it is part of the block that can't change without a significant amount of ETH getting formed. The number of blocks required to ensure that a transaction will be rolled back is called blocks to finality. And time to create the blocks is called time to finality. It is considered to be an average of 6 blocks to reach the finality status, given that a new block is validated each 12 seconds. The average time for finality for a transaction is 75 seconds. So Starknet transaction finality. Starknet, a layer 2 solution on Ethereum, has a two-step transaction finality process. The first step is when the transaction gets accepted on layer 2, and second on layer 1. Accepted on layer 2, when it's acquired by the sequencer and included the block on Starknet, it chooses L2 finality. However, the finality relies on the L2 consensus and comes with a slight risk of collision among sequencers leading to a transaction reversal. Accepted on layer 1, the absolute finality comes when the block containing the transaction gets a proof generated. The proof is validated by the verifier contract on Ethereum and the state is updated on Ethereum. At this point, the transaction is as secure as the Ethereum stake processors can provide, meaning it becomes computationally infeasible to alter or reverse it. Comparison. The main difference between Ethereum and Starknet transaction finality lies in the stages of finality and their reliance on consensus mechanisms. Ethereum's transaction finality becomes increasingly unlikely to be reversed as more blocks are added. Starknet's finality process is twofold. The initial finality L2 is quicker but relies on L2 consensus and carries a small risk of collision. The ultimate finality is slower as it involves generation and validation of proofs and updates on Ethereum. However, once reached, it provides the same level of security as an Ethereum transaction. So rejected transaction. So rejected when a transaction finds validation in the mempool but fails during the sequence validate, it's still rejected. So finality status received, execution status rejected. So we can see the difference between finality and execution status. So handling of reverted transaction. A transaction can be reverted due to failed execution. The transaction will still be included in a block, and the account will be charged for the resource consumed, received, reverted. So transaction life cycle. So we have the mempool. We have the mempool. So if it is valid, it is received. If it is not valid, it is not received. Then if it is valid in the sequencer, it is received. It is not valid, it's rejected. It is received but rejected. So then here it is succeeded, here it is reverted. Succeeded, if it is succeeded there, it is succeeded there, reverted. So any question? Any question? Any question?
Okay, so I have a question. I don't know whether it's relating what to what you just explained. Now, some code base I see gas estimation on their on their tests before their test scripts. Like what is actually that gas estimation doing there?
What?
Hello, sir. Can you hear me?
Yeah, I can hear you.
Okay, I'm asking in some scripts, like in some Cairo test scripts, some define gas estimated gas. Like I want to ask, why do they do that actually?
What? Sorry, I did not get.
I'm asking them some test scripts on Cairo, they define gas estimation like estimated gas.
Okay.
Yeah, I want to ask like why use it? Like why do they do that? Because normally, even without the gas estimation, it will still, the test will still run.
All of those things are they are compiler this thing. They are compiler related. Yeah. So and I think in the latest in most of these latest these things they are not. Yeah. So someone is answering it on the good. This I'm coming. Yeah. So so you say that to grasp you understand this time built-in, yeah. What I was looking for then, I talked about ints. So we also have built-in. So built-in, these are predefined operation in your codes, simplify common tasks or calculation. So we have the following are built-ins: cargo steps, Peterson matches, gain checks, signature verification. B indicates the signal or cost of an operation, showing how resource intensive action is. So components and limits, cargo steps, Peterson matches, signature verification, gain check. Who? DA, data availability. Data availability. It's So data availability is key in blockchain networks, especially in layer two solutions like Starknet. So Rolex acting as a bridge between Ethereum and off-chain computation enables transaction off-chain while maintaining Ethereum security and asset system. The focus often lies on scaling computation and execution, but it's just part of the challenge. Both computation and data aspects are vital for effective blockchain scaling. The growing use of rollups, which facilitates more off-chain execution, intensifies the need for efficient data availability solution. This must arise from the necessity to store, access, and verify data from off-chain transactions. Robust data availability solutions are critical for rollup success. Without effective data handling, the scalability and performance advantages of rollups could be undermined. Base layer blockchains such as Ethereum are evolving towards becoming data availability layer. A prime example of the evolution is Celestia. They have spearheaded this movement by developing a layer one blockchain with a data-centric approach. In parallel, Ethereum is undergoing a significant transition. Historically, an execution-focused blockchain, Ethereum is now incorporating new EIPs to shift its focus towards data availability. So data availability in Starknet. State transition process in Starknet as the most blockchain network. The system transition from the state n to state n plus 1 by executing a series of transactions within a block. In the Starknet case, this is done with the current language. Any current state information. To know the current state n of network, there are two primary sources: the sequencer or the full node. The liveness problem arises from its concern. What happens if both the together and the full node become unresponsive? This will be due to a variety of reasons, such as technical failure or external attacks. If for some reasons both the together and the layer two full nodes stop responding, there will be no way to extend the current state of n of the network. There scenario, while transaction could still be received, the network will be unable to transfer from to state n plus 1 due to the lack of information about the state n. Consequently, the network will essentially become stuck. Although this situation is highly unlikely, its potential impact is significant. It will all depend on the network, preventing any state transition and effectively freezing operations. State difference. Frankly, addresses the liveness problem through the transition of validity pools and state difference to layer one. This process is critical to ensuring that the network remains operational and the state can be verified independently of the sequencer and layer 2 full nodes. So validity proof to layer 1. After completing the validity proof, Starknet sends it to layer 1. State difference as code data. So along with the validity proof, Starknet also sends what's known as the state difference. The state difference represents the change in the L2 state since the last validity proof was sent. So this includes updates and modification made to the network state. So if you look at the way Starknet sends it, apart from the validity proof, it proved that the transaction is correct. So it also sends the state difference. So after state difference, along with the validity proof, Starknet also sends the so it also sends the state difference. So which is going to be, the difference there if there are smart contracts that their storage vehicle and all those things have changed. All those so it's going to send those state difference also. And the data availability and state changes in transaction. So transmitting changes not balanced. So what Starknet sends to layer 1 for data availability are the changes in states, not the new balances. This involves capturing how each transaction within a validity group alters the state. So consider a simple scenario with three participants, Jimmy, Juice, Bruce, and Nick. Transaction sequence. Jimmy sends one hit to Rose, then Rose sends half an hit to Nick. State changes sent to layer 1. The data sent to layer 1 would reflect that Jimmy has one ETH less. Rose has half an ETH more, and Nick also gains half an ETH. The next changes are what matter. For instance, if Jimmy and Rose send ETH back and forth, but the end result is Jimmy having half an ETH more, only these net changes are sent to layer 1. So this one sends this one to this one. So what he's going to do is what Jimmy is going to, Jimmy. Wait, so this is it. Jimmy sends one to this one. This one now sends half to this one. So which means Jimmy has -1, which means that he sent -1 out. Rose received because Rose has already sent 0.5 to another person. So you just count as Rose received 0.5 and Nick received 0.5. So that's the meaning of state difference. If this one is still sending R to this one again, if this one sends 1 to this one sends 2 to this, and this one sends 0.5 to this, you see that this one that sends 1 to this received 2 and then send 0.5 out. So 1 minus -1 plus 2, that's 1. Minus 0.5. So which means that this one is going to be this one is going to be plus 0.5. But this one, it received 1. So we have 1 minus 2, that's -1, plus 0.5, that's -0.5. That's what we have there. So this is the meaning of what state difference. This approach means that even with multiple transactions, the actual data sent for data can be less if the net state changes are minimal. In cases where transaction parties notify each other, so no change in the state occurs. Because nothing is sent to layer 1 for data availability, making it the cheapest form of transaction. Since the cost of sending data to Ethereum as code data constitutes about 9% of layer 2 transaction costs. Reducing the amount of data sent can significantly impact overall transaction costs. Projects on Starknet often use strategies to minimize state changes in their transactions, thereby reducing the data sent to layer 1 and lowering transaction costs. So reducing data availability cost in Starknet. So two main mechanisms to reduce data availability costs are currently under implementation. So we have the EIP 4844 and the violation. So the 4844 is the blob data, while the violation is the flexibility in data storage, which means that you can you can say that, okay, my own data, I'm not posting it on Ethereum. I should need Ethereum, Starknet too. When you make something like that, that's called collision. When you start saying, okay, my own data should remain on Starknet. I don't want to post it on Ethereum. And that's going to reduce the cost of your transaction. I hope that is clear. I hope that is clear. So EIP 4844 proposes a new change in how data availability information is sent to layer one. Instead of using core data, the information will be sent to blobs. This mechanism is cheaper than the current method used by Starknet for posting data to Ethereum. Consequently, it would make layer 2 transactions more affordable. So the notable downside of this approach is the limited life of block data. Once posted to Ethereum, this data will only be available for 1 month before being deleted by layer 1 nodes. So violation introduces the concept of choosing where to store data for transaction liveness. Users can opt to post data either to Ethereum or option alternatives such as data availability committee systems like Celestia or EGIN-DA. The cost of using violation varies based on the choosing storage option. Off-chain options are expected to be cheaper than using AIP 4844. So the timeline for enabling violation on Starknet is not yet determined, but it's starting to follow the support of AIP 4844. AIP 4844 is already eventual for multiple rollouts. Solution offers a unique advantage for Starknet by providing more flexibility in data storage and potentially lowering costs. Prevention of pollution requires having a virtual machine that is not limited by the alliance to emulate Ethereum. So a custom virtual machine like Cairo is required. So replacing Starknet state. This is contingency plan for extreme scenario where the sequencer layer 2 becomes unavailable. So Starknet, like any blockchain network, started with an empty state and a genesis block. Over time, it has processed multiple blocks, leading to changes in its periodically sends a validity proof to L1. So along with the validity proof, as Starknet continues to produce more block, the process repeats. So by applying the state difference in order as they are set to layer one, it's possible to reconstruct the layer two state. So which means that if you want to reconstruct the state in layer in Starknet, you just have to go through all the, you know, just add all the state difference and you're going to get the layer two state. The Starknet OS. The Starknet OS, the last step inside inside the sequencer plays a crucial role in determining why the state difference is the output of the sharp and how it interacts with the. So this one is Starknet shared sequencer, I think. I know that this sharp is name of the book. So the Starknet OS is based on Kairos and other version of them. So the Starknet OS receive four main inputs: the current state, the new block, the class hashes resulting, compiled class hashes resulting from select transactions. So the Starknet OS takes the current state and presses the new transaction and block, evaluates what changes occur in this thing. So here we have Starknet OS, current state, new blocks, class hashes, compiled class hashes. So this one it gives you current state and the new blocks, gives you the state difference, class hashes, compare class hashes, compare class hashes. So the sequencer executes numerous transactions and creates blocks. When enough blocks accumulate, they trigger the creation of validity. These blocks are passed to the Starknet OS to calculate the state difference, class hashes, and compile value. This is the information that the prover is tasked with proving. The output from the blockchain writer, therefore, includes these three elements, state dependent. This output is what gets sent to the memory pages, smart contract, and Ethereum. So the blockchain writer module, contrary to the direct interaction between the prover and the Ethereum verifier, there is an intermediary known as SHA. The prover in Starknet, currently the Stone prover, is focused solely on proving the execution of the cargo program. Internally, Sharp utilizes an externally owned account specifically for interacting with Ethereum. This account is responsible for conducting transactions on Ethereum network, so handling validity proofs and state defense. So the actual module within Sharp that sends the price proof and state defense to the memory pages on Ethereum is known as blockchain writer. So this module bridges the gap between the internal workings of Starknet and Ethereum blockchain. So direct interaction with Ethereum. The output of the prover is directed to the blockchain writer. It is this blockchain writer that interacts with Ethereum, sending data to the final step in data transaction. Blockchain writer is the final step. So the proving data from Starknet internal application is transmitted to Ethereum for storage verification. So this is the Ethereum address of the blockchain writer, which is itself an EOA coding resources. So see sharp. These are already, I guess it transmitted to this most likely. So there's nothing again. There's nothing inside this one again. So you can see that it's no longer, so it has transferred to this one most likely. So I think this is the new sharp. See, 2 hours ago. This is the contract verifier. So data availability modes, roll-up mode, definition of the data for is posted directly on the roll-up mode is posted directly on Ethereum. Advantage, the primary benefits of enhanced liveliness, cost optimization. So Validium, for Validium, data is off-chain. The primary advantage is cost effectiveness, liveliness guarantee, trade-off for reduced cost. So Starknet uses this. Then evolution mode, upcoming, you have the ability to say wherever you want to put it. So do we have questions about that? No question.
There's no question, sir.
All right. Okay. Sequencers. So we've talked about sequencers, right? So before diving in, make sure to check the architecture. So three main layers exist in blockchain: data availability, ordering, and execution. Sequencers have evolved within this evolving modular algorithm. So most layer one blockchain like Ethereum handle all these tasks. Initially, blockchain served as distributed virtual machines focused on organizing and executing transaction. Even local rollups running on Ethereum today often centralize sequencing, ordering, and execution while relying on Ethereum for data availability. So this is the concept of Starknet 2, which is the Ethereum for data availability and centralized sequencer for ordering and execution. However, it's possible to decentralize sequencing and execution as Starknet is doing. So each of these layers plays a crucial role in achieving consensus. First, the data must be available. Second, it needs to be put in a specific order. That's the main job of a sequencer, whether run by a single even sequenced. The final step done by the sequencer to determines the system's current state and keeps all connected lines on the same page. Okay, so introduction to sequence. I mean, the element of layer two solutions like rollups has altered the blockchain landscape, so improving scalability and efficiency. What about transaction order? Is this managed by the base layer or is it an instance system? Instance system. So in essence, sequencing has two quarters, sequencing and executing. So first, it orders transaction, determining the canonical sequence of blocks, then new blocks to the sequence. The execution. So to clarify, we see sequencing as the act of taking a group of another transactions and producing an order block. So the sequencers on Starknet, so we have Madara and Kraken, two high performance Starknet sequencers. So a sequencer must at least do two things: order and execute. So Madara handles the sequencing process, supporting methods from simple FCSS and PGA to complex ones like Nawal and Bosa. Also manages the meaningful, a critical data structure that pulls unconfirmed transactions. So developers can choose the consensus protocol through Madara's use of substrates, which offers multiple built-in options. So Madara lets you choose between two execution crates, Logfire and Starknet in Rust, both with the LVM for their framework. So we also have the Kraken as an option. Ordering it employs Navel and Bushak for multiple management. Guys, choose from multiple consensus methods. So execution, it runs on Starknet in Rust. And it can be deferred to either Cairo native or Cairo VM. So this one's a conclusion. So this is how to get started with Madara. Okay, you can come back to this and read it very well. Then we have the provers. So the sharp is shared prover. Yes, I got it. So generated proof, stack verifier program, Cairo job prover, new proof generated, repeat process, trigger reached, solidity verifier. Conclusion. So we've talked about nodes and the different ways in which they can be. So the Pathfinder node, Juno, Papyrus, I think all of them are developed by Nethermind. Implementing a Pathfinder node, 32 gig, 1 terabyte, gigabyte Ethernet. So these are to run with. Cool. Layer 3 and app chains. So app chains lets you create blockchain design essentially for your applications need. So this specified blockchain allows customization in various assets such as hash functions and consensus algorithm. Moreover, they inherit the secret feature of layer 1 and layer 2. So layer 3 blockchains can exist on top of layer 2 blockchains. You can even build additional layers on top of layer 3 for more complex. So a sample layer is shown below. So you can see we have Ethereum, we have the public Starknet. So on top of the public Starknet, you can build a privacy Starknet. You can build another Starknet that now has a layer 4 Starknet, privacy Starknet. You can build an app-specific Starknet. You can build Stack X, the Validium, Stack X, the rollup. So examples of an environment with a layer 3 and layer 4. In this example, there are 3 options include the public Starknet, which is a general layer 3 Starknet optimized for cost-sensitive application, customized L3 Starknet, StackX systems used by platforms like DYDX and Solana. So privacy focused Starknet. Benefits of layer 3. Layer 3 app chains with Madara as an app sequencer or other option offer a variety of advantages due to its modularity and flexibility. Here's an overview of the key benefits. So quick iterations. App chains enable application protocol changes, freeing you from constraints of the public layer 2 roadmap. For example, you could rapidly deploy new DeFi algorithms to your user base. Governance independence. You maintain complete control over feature development and improvements, avoiding the need for decentralized governance consensus. This enables, for example, quick implementation of user-suggested features. So cost efficiency. So layer 3 offers substantial cost reductions, potentially up to 1 million times compared to layer 1, making it economically feasible to run more complex applications. So we have security and other ones. So Madara as a framework for layer 3 is a framework that simplifies the development of modular app chain. So with Madara, you can leverage the Starknet stack, scalability, and security while tailoring a chain to the specific requirement of your app. So key benefits of developing with Madara: comprehensive control. With Madara, you can customize essential components such as your approval and compiler version, reduce congestion, your app chain sells your dApp exclusively, guaranteeing predictable performance and so you have the Canon also work as a service. Solidity verifier. Before explaining this chapter, review the stack. So quick overview, sharp and sharp jobs. So sharp is the shared prover. So that sharp aggregates various Cairo programs for distinct users. This program each with unique logic run together, releasing a common proof for all, optimizing cost and efficiency. Furthermore, Sharp supports combining multiple pools into one, enhancing its efficiency by allowing parallel pools to process and verification. Sharp verifies most Starknet transactions like transfer, trading. It also confirms smart contract execution. To illustrate Sharp, think of commuting by bus. The bus driver, the prover, transports passengers to the cargo programs. The driver checks only the tickets of the passenger alighting at the upcoming stop. Much like Sharp, the prover forms a single pool for all carry programs in bash, or verifies only proof of programs within the succeeding block. So sharp jobs, known as sharp over jobs, let multiple users present their carry programs for combined execution. So okay, so Solidity verifier. The Solidity verifier is a layer one smart contract crafted in Solidity, designed to validate stack rules from Sharp. So Sharp verifier contract map. You can touch this ones. It's not yes. So there is this new what's it called? There's this new prover that Starknet is building. Is there anyone that knows it?
No.
So how many of you have heard about Circle Stack? Circle Stack. They released a paper recently. So a paper that's on Circle Stack. So and with that, they are building the STWO prover. So that's going to be much faster than this one. It's going to be much faster than this one. So you can see that the chain with the innovation is actually the Starknet, and it's you just have to like deep dive into the ecosystem and also build on it. All right, all right. So you can see the decentralization is still under construction. It's not decentralized yet. I know that the person that asked me the question, like, is centralized? Yeah, like, how is Starknet centralized? Is too bad to hear or what? The sequencer is still currently centralized, and that's not a problem for a layer 2 since the security is on Ethereum. So it is there are plans to decentralize it. So smart contracts, you all know what smart contracts are, right? Abina.
Yes, sir.
So deployment and interaction. So what's the time? We have just 30 minutes left. So I would have said that we should do a little bit of front end integration to it too. Yeah, account abstraction. So do you have any question? Do you have any question? Or
I think no one has a question.
who is that? I'm not saying this thing. If you have a question, just talk, Abby. Okay, nobody has question. That's nice. That can mean two things. It's either you all perfectly understood everything that I said, or the opposite. So which of the two?
Um, let's say it's just a matter of time. Actually, it will sink.
Actually. So the only way it's going to skink, is practice makes what?
Perfect.
No, it cannot be perfect now. How is that possible? So practice makes improvements, right? So as you are reading and reading and reading and reading, but at least from what we actually did today, there should be nothing in Starknet that you don't understand. Let's let's be truthful to ourselves. Hmm? Let's be truthful to ourselves. So this is what we are going to do because so I'm just going to allow you the next 10 minutes to ask any question. Can I just ask any question actually? So we are going to use the next 10 minutes to for you to ask any question. Then we are now going to do an introduction to only those and how you can start, you know, contributing and all of those stuff like that. If you have any question, you can just ask right now. As regards most things, Sha, I don't want to say anything at all because the kind of question that you're asking, I not see anything said is almost so. If you have any question, you can ask. No questions still. Should I be going? If there is no question, I'm not proceeding. It's like
Okay, sir. I don't know whether my question is relating to what we did today, but I'm just
you
like,
yes.
yeah, like I feel like I want to ask actually, like, what does it take for someone to actually, say, let's say, spin up a node on Starknet, like
Spin
to
up
run a
the mood.
like to
Ah,
run a node on Starknet.
yeah, I think everything was. You can come back to this. Where is it? That part that we skipped. You can say that they even put the cost of those hardware and this thing there. So where is it? Sef? Now, it's under this notes. Yes, you can just come back to this notes and start and read it. So you can run the Juno note, the Juno by Mine. I see the hardware requirements, the estimated cost. So it's not even plenty. And yeah, you're good to go. Is that the only question?
From my end, that's all.
Okay. No other questions. No question. Okay. Then so maybe there's going to be most likely another
Hello,
class
sir.
for, yeah.
Yeah. How do you know if this is going to be our last class?
You don't know if,
Do you know if this is going to be our last class?
yeah, there's most likely going to be another for the front end, another for the front end, and that's going to be the last class. This normally is supposed to be, yeah, okay. So we just find a time and we communicate it. So for us to to do the front end part, and that will be all. So yeah, a piece of advice, or yeah, what am I to even give you an advice? Just keep
You
on
be boss, so
for real. So just, you know, just try to like put yourself out there. And the best way for you to put yourself out is by contributing, and the Starknet is still the best framework, the best, is the most rewarding currently that you can contribute to. So you should try to explore the Starknet ecosystem, everything about it, and you'd see, okay, what are those things that you can improve in it. If you don't use it, there's no way you'll be able to say that, okay, there's this problem somewhere that I need to improve that, or I can improve. So all the things that you've learned throughout the start of the boot camp, just apply them. And one thing that you actually need to know is that, see, it is only if you don't need a help, that's when you are not going to say anything. So on Starknet, even if you don't have a job, in fact, you might even be better off not having a job than having. It's just that job gives you this security and peace of mind. So, but if you have that builder mindset, yeah, Starknet is like the most rewarding place that you can ever be. So, and yes, you should also, go on, what's this platform? Only Dust. You know, like there is Starknet, and then there is the Only Dust platform for you. Just go to Only Dust, sign up for. When you sign up, you're going to see different projects there. So of course, before you can start doing this thing, and you don't even have to be genius for you to start contributing there. You just have to have, number one, the curiosity and the willingness to do. That's all. So far as you have the curiosity and the willingness to do, go to Only Dust, look for any program, look for any what's it called? Look for any project that you can contribute to, and look for any issue there. Tell them that they should assign it to you. And one thing about it is that when you do that, everything, like the resources that you need for you to be able to do it, they are going to provide it for you. So you just have to, and if you have problem while executing it, you can reach out to them, you can reach out to your friends and all. So those are the ways in which you are going to become known. So right now, you know I know most of you just finished the Web3 class, and now you're just finishing the what's it called? You're just finishing the master class also. So so you should just what's it called? I'm going to stop the recording soon so that I can say some other things. So you should just make sure that go to Only Dust and start contributing there, and you're going to be rewarded for every issue that you are contributing to. Okay, someone has a question. What's that?
I think I'll just say it after you're done. So you stop recording.
Okay.